Have you ever wondered how energy really travels in electrical circuits? We flip a switch, and instantly, a light bulb illuminates a room. It seems almost magical, but the explanation is far more fascinating than you might imagine. This simple act of turning on a light hides a profound truth about the nature of energy and its transmission. Many believe that electrons, those tiny particles zipping around atoms, are responsible for carrying energy through wires like miniature delivery trucks. This idea paints a picture of electrons as busy workers, each one diligently transporting packets of energy from one place to another, ensuring our devices function smoothly. This is a common misconception. The reality is far more intricate and fascinating. While electrons do move in a circuit, they are not the primary energy carriers. Instead, the energy transfer in electrical circuits is more about the electric field and the potential difference across the circuit components. They play a crucial role, but their movement is more akin to a slow, jostling dance than a high-speed energy delivery service. Imagine a crowded dance floor where everyone is bumping into each other, moving slowly and randomly. This is a more accurate representation of how electrons behave in a wire. The energy is actually transferred through the electric field that propagates at nearly the speed of light, not by the slow drift of electrons themselves. Understanding this distinction is key to grasping the true nature of electrical energy transfer. To understand the true nature of energy flow, we need to turn to the brilliant mind of James Clerk Maxwell, a pioneering figure in the field of physics. Born in 1831 in Edinburgh, Scotland, Maxwell's contributions to science have left an indelible mark on our understanding of the physical world. Maxwell was a 19th-century Scottish physicist whose work laid the foundation for much of modern physics. His curiosity and intellect led him to explore the fundamental forces of nature. Maxwell's equations, a set of elegant mathematical formulas, unveiled the interconnected nature of electricity and magnetism. These equations are not just abstract symbols, they represent the very fabric of our universe. Maxwell showed that these two forces are not separate entities but rather two sides of the same coin: electromagnetism. This groundbreaking realization was a monumental leap in our understanding of the natural world. Maxwell's equations predicted the existence of electromagnetic waves, disturbances in the fabric of space-time that travel at the speed of light. These waves are created by the interplay of oscillating electric and magnetic fields which dance together in a harmonious symphony. Imagine the electric field as a conductor and the magnetic field as the orchestra, creating a beautiful and intricate performance that propagates through space. These waves propagate outwards like ripples on a pond, spreading energy across the cosmos. Light itself is an example of an electromagnetic wave, a phenomenon that Maxwell's equations helped to explain. This revelation was profound, as it connected the behavior of light to the fundamental forces of electricity and magnetism. Light waves carry energy across vast cosmic distances, illuminating the universe and enabling life as we know it. From the warmth of the sun to the glow of distant stars, electromagnetic waves are the messengers of energy, traversing the vast expanse of space. Maxwell's work not only deepened our understanding of these waves, but also paved the way for countless technological advancements. Today, we rely on electromagnetic waves for communication, medical imaging, and even exploring the far reaches of the cosmos. The legacy of James Clerk Maxwell's marvelous waves continues to resonate, shaping our world in ways he could have only imagined. Building on Maxwell's groundbreaking work, John Henry Poynting, a British physicist, developed a concept known as the Poynting vector. This vector, a mathematical tool, describes the direction and magnitude of energy flow in electromagnetic fields. The Poynting vector points perpendicular to both the electric and magnetic fields, indicating that energy flows in a direction perpendicular to the motion of charges. Section 5. Debunking the myth: energy's true path. In this section, we will delve deeper into the true nature of how energy travels in a circuit, debunking common misconceptions, and providing a clearer understanding of the underlying principles. Let's revisit our light bulb example. This simple yet powerful illustration will help us grasp the fundamental concepts of energy transfer in electrical circuits. When you flip the switch, you create a closed loop or circuit. This action allows electricity to flow, completing the path needed for the light bulb to illuminate. This circuit allows for the establishment of electric and magnetic fields around the wires. These fields are crucial, as they play a significant role in the transfer of energy. These fields, not the electrons themselves, carry the energy. It's a common misconception that electrons travel from the switch to the bulb to light it up. In reality, the energy is transmitted through the electromagnetic fields surrounding the wires. Imagine a garden hose filled with water. This analogy will help us understand the concept of energy transfer in a more tangible way. The water molecules represent the electrons in a wire. Just as water molecules are already present throughout the hose, electrons are present throughout the wire. When you turn on the faucet, you don't have to wait for the water molecules from the faucet to reach the end of the hose to start watering your plants. The water flows almost instantly because the pressure travels through the hose. The pressure, which is analogous to the electromagnetic field, travels much faster, instantly pushing the water out at the other end. Similarly, in an electrical circuit, the electromagnetic field propagates quickly, allowing the energy to be transferred almost instantaneously. The light bulb lights up because the energy carried by the electromagnetic fields reaches the filament, causing it to heat up and emit light. This process happens in a fraction of a second, demonstrating the efficiency of energy transfer via fields. It's important to note that while electrons do move, they do so at a much slower pace compared to the speed at which the electromagnetic fields propagate. This slow movement of electrons is often referred to as drift velocity. Drift velocity is the average speed at which electrons move through a conductor when subjected to an electric field. This speed is relatively slow, often just a few millimeters per second, whereas the electromagnetic fields travel at a significant fraction of the speed of light. Understanding this distinction is crucial for comprehending how energy is efficiently transferred in various electrical devices we use daily. From light bulbs to smartphones, the rapid propagation of electromagnetic fields ensures that energy is delivered swiftly and effectively. This principle also applies to larger systems, such as the power grid. The energy generated at power plants is transmitted over long distances through power lines, with electromagnetic fields playing a key role in this efficient transfer. In summary, the true path of energy in an electrical circuit is through the electromagnetic fields surrounding the wires. This understanding helps us appreciate the sophisticated and efficient nature of energy transfer in both simple and complex electrical systems. By debunking the myth that electrons themselves carry the energy, we gain a deeper insight into the fascinating world of electromagnetism and its practical applications in our everyday lives. Thank you for joining us in this exploration of energy's true path. Section 6. Power lines in the sky, a matter of energy flow. You may have noticed that high-voltage power lines are always suspended high above the ground. This is not just for safety reasons, it's also about maintaining the efficiency of energy transfer. The Earth, being a conductor, can interact with the electromagnetic fields surrounding power lines. Section 7. The Earth's dampening effect. This interaction can lead to energy loss through a phenomenon known as ground loop currents. These currents dissipate energy into the Earth, reducing the efficiency of energy transmission. By elevating the power lines, we minimize this interaction and ensure that most of the energy flows directly to our homes and businesses. Section 8. The importance of understanding energy flow. Understanding the true nature of energy flow in circuits is not just an academic exercise. It has practical implications for designing more efficient electrical grids, developing new technologies for wireless power transfer, and even understanding the vast energy flows that occur in astrophysical phenomena. Section 9. Beyond the wires, energy in the universe. The principles we've discussed extend far beyond the confines of our homes and electronic devices. Electromagnetic radiation, the very essence of light and other forms of electromagnetic energy, governs the interactions between stars and planets, shapes the evolution of galaxies, and allows us to communicate across vast cosmic distances. Section 10. The future of energy transmission. As we delve deeper into the intricacies of electromagnetism, we open doors to new possibilities. Wireless power transfer, a technology still in its infancy, holds the promise of freeing us from the tyranny of cords and cables. Imagine a world where our devices charge wirelessly, drawing energy from the surrounding environment. Section 11. The answer to the enigma. So, how does energy really travel in electrical circuits? The answer lies not in the movement of electrons themselves, but in the invisible dance of electric and magnetic fields. These fields, propagating outwards at the speed of light, carry energy with them, illuminating our world and powering our lives.